So similar to MySQL, we have different probe sets. In fact, the query probes, the names are the same. We have a little bit different argument. But I think going forward, the probes that will make sense and make them generic, we'll try to make sure that they're the same for both MySQL and PostgreSQL. So again, we have the probes, to figure out how to measure the time for the query, the entire query, or just for part of it, parsing, planning, or execution. And we have probes for sorting, storage management. That means you can figure out the buffer reads, buffer write, hit and misses, and then checkpoint and locks. So like I said, we have about 54 of them right now, and in the next release we'll plan to add some more. Okay, so I'd like to do some demos with the probes. Okay, so what I'm going to do is I'm running this DTrace script. What it does is it just tells you how many times a SQL statement has been executed, or same SQL statement. So I have this simple script that shows the different select updates operations. So I'm going to run it. Okay, and I'm going to come back here, type Control-C, and it tells you exactly how many times the SQL statement has been executed. So it's it's not very interesting. But it gives you some useful information. So what we're going to do next is actually determine the time it takes to execute the statement. Okay, so I have a different DTrace script. So this one is query time. So I'm running the DTrace script again, and we'll run the same query here. Okay. Okay, so it tells you the time. The time is actually in nanosecond. So this particular select statement, it looks like it's doing, what is it, about 231 millisecond. So okay, so that this is kind of taking the most time to perform. What you could do is you can actually drill down further to find out what is going on in the select statement, right? So what I'm going to do is I have another script that actually drill down and try to find out what's going on with this query. So I'm going to run this script here called query trace. Okay, and I'm just going to cut this one. Okay. Okay, there we go. So look at the data. You can see here. So this showed the buffer reads for all the tables that's been touched for this particular select statement. And as you can see over here, look at this table. There's more than 8,000 buffer reads. Okay, so what does this number mean? So we can actually find out which table this number 16 is actually an object identifier for the table 16397, which table that is. And here we also show like the time it took to execute 5.7 seconds. And it also give you additional information here about the buffer cache hits, or the misses, and then the time it actually took to read, from cache and the time it took to read from the disk. Okay, so let's find out what's going on here. So I'm going to get out of this. So first, we have to determine which table it is, right? Okay, so what's the number there? 16397. You might have guessed that it's that table, right? The pgbin account table. Okay, so let's quickly take a look at this table. Okay, as you can see, we're selecting on this column a balance that doesn't have an index, right? And that's why it took so long to run this select query. So what if we create an index? I got this script here. Okay, so we created the index, and okay, so there's an index there. So let's just rerun that query again that we ran the first time that took more than 5 seconds. Okay, actually before that, I have to run the DTrace script again. Okay. So let's see what kind of information we have here. So as you can see, the same table here, there's only 7 buffer reads because of the index. And if you look at the time, now it took 0.076 seconds to execute that same query versus 5.7 seconds. And there's a lot of buffer. I mean, there's just a few reads to the buffer cache. The number is a lot less than what you saw before. Okay, so that's just kind of a pretty simple example of how you could use the probes in PostgreSQL to identify some performance problem. The next thing I'm going to do is, so you've seen some DTrace script. How many of you think that it's cryptic or difficult? Actually, at first glance it looks kind of difficult, but once you get used to it, it's not that bad at all. But one thing you could do is there is a GUI tool that allows you to display DTrace data graphically, and I'm going to quickly show you that. And we did some integration with the probes in Postgres so that you can just run the GUI tool and be able to look at interesting DTrace data without having to write any DTrace script at all. Okay, I hope you can see this. So what I'm going to do is I'm going to run a workload that generates some activity. Okay, this is a simple workload called pgbench. And then I am going to run this particular script here, which is kind of display the lock contention within Postgres itself. So as you can see, it shows you the locks. These are the exclusive locks, and it shows you how long the Postgres server has to wait to acquire this lock. So pretty much it tells you which one is the hot lock within the system. So we use this kind of information to tell the PostgreSQL developer what to do with this lock, whether to split the lock to reduce the contention so that it will improve the performance in Postgres itself. So DTrace right now, runs on Solaris, Open Solaris, Mac OS, FreeBSD. Unfortunately, it's not on Linux yet. But the thing is, when you have probes like this and you can identify performance issue, and when you fix this issue, it actually helps people who run PostgreSQL on other platforms as well. Okay, so that's pretty much the demo I want to show for PostgreSQL. So I will go back to the slide. So in summary, if you saw in the presentation, there are two ways you can observe user application. One is through the use of the PID provider, which means that you don't have to do anything at all to observe the application. So you can observe the application using the function name. But the drawback is that you have to understand the application and know what the application does. And the other way is through the use of custom probes. Okay? So if you're application developers, if you know the code pretty well, adding DTrace probe is pretty easy. And by doing that, you actually expose these interface to your end user. Okay, so with DTrace probes, once you have the probes in place, solving performance problem is actually pretty easy. It could be done in minutes versus days if you didn't have the probe. So again, adding DTrace probe is actually pretty straightforward. I mean, at first impression, it might look difficult, but it's really not that hard at all, as you seen here. And so what we're going to do is we'll provide all the scripts, the demos that we have here on our blogs. So if you're interested in trying out, definitely go check out blogs, and we have the link here. And there's a lot of other resources about DTrace. And if you're interested in learning more about the kind of the nitty-gritty of how DTrace works, there's also information here. All right, so that's the end of our presentation, and we will open up the questions. Can you walk to the mic, please? Yeah, so there, in these probes, when you compile the probe definition file, it actually generates two macros. One is the probe that you would insert, and they have another one's called enable. So if you have a probe that needs to evaluate a very expensive argument, what you would have to do is put that enable check in front, and that will actually prevent the argument to be computed at all, and that will pretty much avoid any performance penalty when the probes are not used.
I was wondering if the code, when you essentially add an active probe to your system, essentially you're adding the probe to your system. What if we run the same code on a non-DTrace OS? If we run either on an OS where DTrace is not enabled, or another OS which is not DTrace enabled, can we use the same code?
Yes. But I mean, when you compile the application, when you compile the application, you obviously have to compile the DTrace probe components. So if it's on a platform that supports the DTrace probes will be included. On a platform that doesn't support DTrace probes, the probes are not added, and in actual, they will just not even be inserted into the binary at all.
Okay, so it is a conditional compilation.
Yes.
So actually, it's a flag. It's if you're familiar with the configure, right? So you do a configure, and to enable the probes, you have to specifically say enable DTrace. Okay, that will actually generate the appropriate macros and make the probes available. And if you don't do that, the macros will still be generated, but they're pretty much translate to no ops.
Yeah.
So on a non-Solaris environment, you'll still see the macro, but the macro will just translate to no ops.
So it's really the converse of using log4j is debug enabled, and the trace happens, it's not labeled.
Yeah.
There's no
Yeah.
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 I noticed, last time I checked it, was almost just one C program. So basically, because of the simple mangling in C++, so
Yeah. You can.
Can you repeat the question?
Yeah, the question is about adding probes into C++ applications. You can add probes into C++ applications. There's no problem. Yes, there is a demangling, but actually if you're adding user-specific probes, obviously MySQL is a C++ application. If you're adding user probes, the demangling, the mangling of the names doesn't happen because you're adding probes with a specific name. If you need to demangle, you can demangle with C++ filt when you're outputting, and you can do that on a PID provider. So on a non-custom probe, you can demangle the C++ names that way. But if you're adding your own user probes, the fact that you would normally get name mangling of the probe names does not exist because you're adding specific name probes into the system. Okay. Actually, it doesn't. It's a very interesting thing. It doesn't have to have symbols enabled. You can even strip the symbols and it will still identify the correct function names within the probes on a PID provider. Okay. Magic.
There's a...
There is actually. If you go in and have a look at how DTrace operates, you'll find out how it does that. It's to do with the way DTrace and operating systems that have DTrace enabled actually execute the application.
Yeah, this is Usenik's article that actually talks about that. It's a pretty interesting idea.
It is magic. I mean, I don't want to pass it off as anything else. They've been very, very, very clever. They have been very, very, very clever, actually, if you have a look at how they've done it internally. But the same part of the system is this whole thing about if you haven't actually enabled the DTrace probes, they have no performance hit. You know, it's all part and parcel of the same system. They tried to invent a way of adding probes that would actually just not do anything if you weren't looking for them. Which is what makes it very, very different from what most people are used to from a developer standpoint. You're used to producing a debug version of a binary and then using the debug version to get the information out. And with DTrace, you don't have to do that. You don't have to create a debug version, and you can do it on a live one without changing your application. With MySQL, the probes are enabled on a DTrace-enabled system. All you have to do is run the DTrace script in order to get the information out. You don't have to switch MySQL off and start it up again in a different mode or anything. It's just there.
Okay, we have less than 2 minutes left, so let's take this last two questions.
What is the actual runtime overhead of DTrace?
It's dependent on how many probes you are looking at. And I can't say anything simpler than that. If you are looking at fairly basic probes in MySQL, the performance overhead of MySQL itself, you're looking at 1 or 2%. If you go down and have a look at every time it looks at an individual row operation, yes, you can kill the performance of MySQL, but that's just because you're then looking at imagine doing a select on a 10 million row table and it's looking at 10 million rows. That's going to be 10 million probes that are going to fire for each time, which somehow the system has to handle. So it's entirely dependent on how many probes you're actually looking at. And I can't give you a specific figure because it depends on... Yes. And the probes you're looking for, because that's the important part. It's not what probes are in the application, it's how many times you're looking for them in the DTrace script.
Yeah. Okay. The last question, yeah?
I have a question about compatibility for building an executable. Let's say if you were moving it from one system to another, is there any chance that the DTrace will be incompatible?
No. Yeah. If you compile a DTrace application and then you deploy it from obviously from the same operating system, Mac OS X to another Mac OS X system, the DTrace probes will still be in there. They will still work. They will still be enabled. You don't have to worry about differences in libraries and anything else complex. No.
Right. So I have the probes in PostgreSQL. It works on Solaris and it works on Mac OS X here. Same probes.
And similar, it works on Solaris and Open Solaris, right? Okay,
Yeah.
You don't have to compile it differently on Solaris and Open Solaris.
He was asking, if you go from one version of EOS to another, and all this stuff.
No,
Yeah.
it all still works.
Still
yeah.
works. Okay, so we're running out of time.
Perfect.
So this concludes session S308356. Thank you.